In this video, we discuss the most common application of differentiation, which is projectile motion. Most of us, when it comes to projectile motion, might think of like playing catch or something like that. Like here's one person throwing a ball with some initial velocity. That initial velocity has a component that's horizontal, it's parallel to the ground, and also has a component that's vertical and sort of in the same direction that's parallel to like the person's body. That's not what we're talking about here. This is the two-dimensional case. We're just going to start with the one-dimensional case, and then we'll generalize to the two-dimensional case. And the two-dimensional case is something that we usually discuss in Physics 1, and we also discuss it in Calculus 3, multivariable calculus. But the concepts are the same. So let's say you start with a ball with some initial position. And that's given to you. We're going to call that initial position y naught. And then we also know the initial velocity. And that's b naught. And if b naught is positive, we're imagining we're throwing the ball upward. If the b naught is negative, we imagine we're throwing the ball downward. If somebody says that they dropped the ball, that means b naught is 0. So we're just taking it at some height and then taking our hand away. So we know the position, we know the velocity at time t equals 0. And our goal is to find the position function. Since we're talking about position in this vertical direction for this one-dimensional example, we're going to call our position function y of t. And that's going to be in some number of units or some kind of unit. Those units are usually meters or feet. If we're on Earth, the units for acceleration due to gravity are 9.81 meters per second squared, and that's represented by this lowercase g, approximate. And of course, in feet, gravity is 32 feet per second squared. So depending on whether your problem statement deals with measurements in meters or measurements in feet, you're going to use either this gravitational constant or this gravitational constant. So we know our initial position, we know our initial velocity. We assume that we're dealing with the acceleration due to gravity, so that the only force acting on the ball is the acceleration due to gravity, or is due to this acceleration due to gravity. And we say, okay, well, how do we find y of t? Well, one way that we can do that is sort of differentiation backwards. I know this is a little bit, we're getting ahead of ourselves a little bit. It's sort of for unit 4, but let's say we know acceleration is g, which I'm just going to use this 9.81 meters per second squared. So I'm going to say that that's in meters per second squared, but it could be in feet per second squared or some other number of units per second squared. And I want to find velocity. Well, acceleration is the derivative of velocity, and velocity is the derivative of position. And you might say, how do you even know that that's true? Well, let's look at position as a function of time, or excuse me, velocity as a function of time. Well, velocity is instantaneous change in position with respect to time. So it's defined to be the limit as delta t goes to 0 of that position at t plus delta t minus the position at time t, all divided by delta. So that's going to give you some units of distance in the numerator divided by units of time. So it's just a change in position over change in time. Change in position is also known as displacement. We've got displacement per unit time, and we want it instantaneous. We want it at a particular moment in time, which requires us to take the limit as delta t goes to 0. That's the definition of velocity. Now, in practice, I don't actually use this. We have a tendency to just compute y prime using our differentiation rules. We take the derivative of this. Well, that's acceleration. And that involves taking this limit as delta t approaches 0 of the velocity at t plus delta t minus the velocity at t, all divided by delta t. But that's, the units in the numerator are meters per second, let's say, if our distance is meters. So this is going to be meters per second, or meters per second squared. So that's saying every second, the velocity is changing by this number of meters per second. So when I see 9.81 meters per second squared, what I'm thinking is every second that velocity increases by 9.81 meters per second. So start with some velocity. A second from now, it's going to be 10 more than that velocity. A second after that, it's going to be 10 more than that velocity, and it's just going to keep increasing by approximately 9.81 meters per second every second. That's what that says, or you can use the 32 feet per second squared if you're working with feet instead. But again, in practice, what we do is we take the derivative of position to get velocity, and we take the derivative of velocity to get acceleration. We don't use the limit definition, but we could. What's nice about the limit definition is that it implies our units, that these are units of position per unit time, and these are units of meters per, or units of position per unit time. Now, since velocity is the first derivative of position, we could also just take the second derivative of position to get acceleration. So, okay, we know all of that's true. And we know that our acceleration is this constant, approximately constant value g, which is usually 9.81 meters per second squared, or this 32 feet per second squared, but it could be some other value. The question is, or actually it's going to be negative g. If we treat this as the negative direction and we treat this going upward as the positive direction. I guess we should also specify our origin. So I'm going to say that y equals 0 is ground level, and then going up is y positive. Those are positive values for y, and then below ground level is going to be negative values for y. This is the positive y-axis. So if this is the positive y-axis and gravity is going in the opposite direction, then we're going to use negative g for the acceleration due to gravity in some number of units per second squared. And you just ask yourself, well, what function has as its slope or its derivative just this constant? Well, a linear function always has a constant slope. So it turns out that the velocity is just that negative gt plus some constant, because I can take the derivative of any constant and get that, or the derivative of that any constant, excuse me, and get 0. So turns out that that constant is v naught. And then if we think through, okay, well, how can I take the derivative of something and get this? Say, oh goodness, it's a constant times t. What do I take the derivative of to get a constant times t? And that turns out to be this negative 1/2 gt squared. And then the antiderivative, or again, the derivative backwards for this piece is, well, I say I've got a constant here. What do I take the derivative of to get the constant? That constant times t. And then we need to add some constant, because the derivative of a constant is always 0. And it turns out that that constant should be the initial y value. And this v naught is the initial velocity. And if you're saying, how do you know that that's the initial velocity? And how do you know that that's the initial y value? Well, you just think about what would happen if you plugged in t equals 0. Plug in t equals 0 here, this is going to be 0, and this is going to be 0, and you should get y evaluated at 0, which we denote by y naught. So that's our initial position. And then you think, okay, if I plug in t equals 0 here, what should that constant be? Well, it should be the velocity at t equals 0, which we denote by v sub 0. So this is kind of a preview of what we call anti-differentiation, working backwards. But basically, we're just trying to use those differentiation rules in reverse. We say, okay, what's the derivative? Or what would I have to take the derivative of to get a constant? Well, a linear function. What would I have to take the derivative of to get a linear function, a quadratic function? And so those are our functions. The textbook uses the notation s of t rather than y of t. I've chosen to use y because I'm using that for the vertical direction. And when I go to the two-dimensional case, I like to think of this direction as x of t, or this direction as being represented by x of t, and this direction as being represented by y of t. So rather than using s, we're going to use y of t here. But this is our position function. If this is in meters per second, or meters per second squared, this is in meters per second. And then this would be in meters. And if we're in meters per second squared and we're on Earth, that's going to be approximately 9.81 meters per second squared. That's our acceleration due to gravity. And the sign just comes from the fact that gravity is pointing in the opposite direction of what we traditionally think of as that positive y direction. Okay, so we know that this is true. We know that the derivative, if this is position, velocity is the first derivative of position. And acceleration is the derivative of velocity or the second derivative of position. There's another one which doesn't come up very often, but you can take the third derivative. We call that jerk. It's the derivative of acceleration. But the jerk in this case is 0. Because if I take the derivative of a constant, I get 0. The first derivative of acceleration is the second derivative of velocity, which is the third derivative of position. One other function that's common in projectile motion problems is the speed function. And usually this is represented by a Greek letter nu, which kind of looks like a V. It's just the absolute value of velocity or the absolute value of y prime. Speed is always non-negative. Velocity can be positive or negative. When we look at this definition of velocity, it's change in position per unit time. So this change in position could be positive or negative depending on whether you're going in the forward direction or the backwards direction. If you continue to go in the positive direction, your change in position is positive. If you continue to go in, if you go from a y value up here to a y value down there, your change in position is negative. Or we say that the displacement is positive or the displacement is negative. Here we're just taught speed is about the change in I don't want to say position. Change in distance per unit time. So I would just say just take the absolute value of velocity. That's what gives you the speed. So with all of this in mind, we can graph this. Let's look at y of t equals this -1/2 gt squared plus v naught times t plus y naught. If v naught is not or is non-zero, then the maximum value on your parabola is going to be some point to the right of where you started. So let's say at some time t equals 0, you're at some initial height y naught. Then your graph is going to look like this. And this, we'll call this T max, or no, actually not T max. This is Y max. And this is the corresponding T value. So this is T at Y max. Corresponds to that location. This is T max. That's how long the projectile has been in the air. This is Y as a function of time. And this is our t-axis. And one thing I want you to notice is that if the velocity is positive, then the graph goes up before it goes down. If the velocity is negative, then actually that vertex of the parabola would have been on this side, and we're just sort of throwing it down. And if velocity is 0, then the vertex would just be right here where we're starting. So let's say that's what it looks like for velocity positive. If velocity is negative, it looks like this. And the rest of the parabola is somewhere over here.